Hi, myself Muhammad Amin with my group mate Muhammad Rajab Ali. We have done with the project of power transfer and voltage profile improvement using Thyristor controlled series compensator TCSC under supervision of Dr. Ahmad Ali Shah and co-supervised by engineer Mahnur Mughal. This is the outline of our project. First of all, I would be introducing it, then what's the motivation, problem statement, literature review, aims and objectives, and methodology. And further in, I would be explaining on power system with TCSC, its location, its equations, mathematical modeling, simulations, and location of power system with respect to TCSC, results and its discussion, future recommendations, and the references. This is the outline of my project presentation. So starting with the introduction, as we have observed, we faced a we have interconnected power system. Power is transferred from long distances and has have a generation at one point, and by covering a long distance, distribution and utilization is far away. So uh, in the distance between them, we faced low voltage profile uh, and lots of other issues. So, keeping in view these issues, we are basically improving voltage profile and the power losses of transmission line. So, in this case, we are inserting a thyristor controlled series compensator, a sort of compensator providing capacitive reactance in series with transmission line, which is basically compensating impedance and improving voltage profile and power transfer, and also improving power transfer capability. So moving ahead, what's the motivation behind this that motivate us to do this project? First of all was the controllability. Controllability was the major factor. By controlling thyristor angle, it was possible for us to control basically its mode, whether capacitive, inductive, whether to insert or bypass TCSC. So the third one was, second one was the automation. It was completely automated. Further, I'll be explaining. It's an also wide range of application now for coming days. Flex devices are going to be the most of the use will be there with C because they are doing compensation and they are even replacing transformers. So we have seen it's a huge research scope. That's why we choose to uh, have this project. This is the motivation. So what is the problem statement? As I have already explained in introduction that uh, uh, for long area of power, long region and long distances of power transfer, and also interconnected system, we have issues like power losses, low voltage profile, and power instability. So, keeping in view all these issues, we are basically proposing our solution, which is the TCSC facts devices. In facts devices, we are using TCSC to basically reduce the losses. So, this is the problem statement. So, moving ahead to the literature review, basically in the first paper we studied about thyristor controlled series compensator has have how it has a controlling mechanism with the specified amount of active and reactive power compensation in between first of all two bases. So for in the next paper we studied about the series compensation of transmission system by controlling TCSC and transmission system design. Also we studied how it has capability to improve basically transient stability of power system. In the next paper, we studied about capacitor series compensator when it used in the transmission lines to basically increase its power transfer capability. So also we also studied the series role of terrestrial controlled series compensator and its impedance compensation, how it basically going to do. So in the next paper, we studied about the system stability in the power system, and we are using TCSC. Uh, Also, how it provides needed reactive power while embedding it into the transmission line. So in the next paper, we studied about both the capacitive and inductive reactance that is being going to be compensated because for the system at no load, we are going to operate TCSC in inductive mode where it is providing basically the um, XTCSC impedance it's providing at no load. At full load conditions, in most of the cases it happens, and we are expecting also that we'll be operating a TCS in the full load conditions because most of the cases we have full load. How it will be operated in capacitive and reactive mode. Also this paper presents conceptual study adopted in the value of capacitor inductor. We are also interpreting from this paper. So when so in the next paper, how we are basically going to synchronize our capacitance with the voltage profile because also overshoot and oscillations are also going to occur. So by considering as a reference of line current how TCSC is going to be the first order lag element system uh, in our series compensation. So in the next paper we studied about the implementation of its controlling mechanism, how basically controlling is going to be operated while PID controller, PI controller, and we did comparison in this paper. So in the next paper, we have studied about power transfer capacity, how it's going to be improved of the lines, limited due to some of the, it has limitations due to some, issues and maybe due to impedance, surge impedance. Also, how this parallel and series compensation of X devices are going to reduce power losses, how it's going to increase its efficiency. We actually studied its comparative analysis of X devices. For the next paper, we study real and reactive powers and the voltage profile out there and how much they are going to improve for the power transmission lines. By placing UPFC and TCSC, we did comparison in between them, and we got a solution that TCSC is more better and simpler than UPFC. So it's the aims and objectives of our project. First, we have designed two bus TCSC, and then we extended it to 14 bus system. Then next in the next we aim to compensate its impedance and the design of the TCSC. And now next is by using TCSC in our 14 bus system and two bus system, how voltage profile is going to improve, and also how we are going to reduce power losses, and also how we are getting more system as unstable and secure. These are the aims and objectives that we have attained. So methodology that we are going to follow, first of all, we collected about the idea of our project, and we find it's hard requirement to basically do this because it's need of area of research and it's going to be beneficial more. So first we collected idea of the project, then we did its literature review, and then we did its mathematical modeling, then we did a TCSC design on MATLAB simulation, then we moved to basically two bus system of MATLAB Simulink. Then we extended it to 14 bus system, and then we synchronized it with TCSU 14 bus system, and then we did its analysis, and we collected some results. On the basis of this, we are basically interpreting. So moving ahead, uh, I will be explaining its equation. Basically, this is the most key equation of our project. Here P is equals to V1 into V2 divided by XL minus XC. XL is basically the transmission line impedance, and minus is getting by XC. XC is the impedance compensated by the by the capacitor, which is getting minus from this XL of transmission line. So V1 is the voltage at one end, and the second end, and V2 is the second end voltages, and this is the alpha 1 and alpha 2 is the conduction angle in between the two ends. So basically, when we are embedding a capacitor in its series, it's basically going to reduce the overall impedance of transmission line. Here you can see in the denominator XL minus XC. So as will having reduced impedance, reduction of impedance or power losses will get reduced, and power transfer, the secondary power will get improved. So in the next equation, Z is equal to 1 over omega C minus XL. It shows when it's greater than 0, it works in capacitive mode, and when it's less than 0, it operates in inductive. So and next, in moving ahead, it's mathematical modeling. This is the typical equation of a capacitor by using as a series current IS, and this is IT, the total current that is following through this switch and inductor. So this is the capacitor voltage and inductor current equation. And next is the IS relation, I am cos omega t. Basically, this is the current which shows the IS going through this in parallel with this basically this inductor. So here we are dividing our TCSC to operate in basically 4 time period. First is T1, T3, and T1, T2, T3, and T4. And our TCSC is on in between T1 and T3. And for T and T4, T2 and T4, it's getting off. We are basically going on and triggering at T1 and T3. And for T2 and T4, our TCSC is off. So this is the typical final equation of impedance calculating TCSC. This is the typical equation from where we are calculating impedance regulated by TCSC. So this is a flow diagram in a TCSC power system. Here basically we have AC source, then a typical power system has a transformer, then transmission lines. So in series with the transmission line, we are basically embedding a TCSC FETs device. So, and here is its control. This is the typical flow diagram of our project. Here in series with this power system, we are basically embedding TCSC. So here is the 3-phase design of TCSC. This is basically shows how basically it's in basically 2 anti-parallel thyristors, and in series with this we have this inductor. So this is and in parallel this is a capacitor. So this is a complete TCSC model for 1 phase, and for the second, and for the third. So this is 3-phase basically TCSC design on MATLAB Simulink that we did. So this is a 2-bus typical 2-bus circuitry of a 2-bus system. Here we have a programmable voltage source 1, then we have transmission line, then we have bus 1, and this is bus 2. Here there is no load is connected. So in series with this, we are basically just embedding this TCSC. So this is basically the reference that we are setting. That this is the value of preset that we are setting it at almost 128. So this is the current voltage and current that we are getting, it's measured, and we are providing its user reference. So basically by controlling by performing some control action of PI controller, it's then fed to the firing unit by generating a TCR pulses. From here, from this firing unit, basically it's providing pulses to thyristors to basically operate in specific time periods. So this is the scope structure, and this is how our TCSC 2-bus system power system is basically working. Let's see its output that we get. So this is 2-bus system TCSC results. So this much impedance first at 0.4, I think yes, 0.5, we are triggering it, TCSC, this TCS, and you know how much it's regulating almost 128 ohm impedance, that TCSC, which is regulating. So in result of this much regulation of impedance, basically at point 0.5 it's basically triggered, and we have seen before triggering of TCSC power is being transferred, it's almost 180, and when it's triggered after some transient period, it's going to be stability in stable mode, and power is getting transferred is almost uh, approaches to 500. So this much increment is we are getting after embedding TCSC in series with our two bus power system. So 128 is the almost impedance that is going to be regulated. So this is the result of two bus power system. Then basically we are we are basically extending it to 14 bus system, and here at 6 and 13 we are embedding our TCSC here. So this is the model of 14 buses, IEEE 14 bus system that we have made, and according to their literature review we have studied, we are basically embedding our TCSC in between 6 and 13 bus out of 14 bus. This is the structure that we have designed, and we also have designed a TCSC and implemented here in between 6 and 13. This is the VRMS voltage without TCSC that we are getting basically. So this is IEEE 14 bus system without TCSC. Basically, this is the voltage VRMS we are getting is 150 degrees centigrade. Let's see when what's the power we are getting without. This is the also this is a voltage waveform without TCSC, and also this is power, active power graph that we are getting. It's almost below 18. 17 point something, 17.23, I think 4. Yeah. Active power, this much power is getting transferred. So now we are connecting TCSC, and at point 4 we are basically triggering it. 150 was being transferred without TCSC, and after some transient it's basically going to get stable at, and power is getting transferred almost it's 170, almost 170 kV kilovolt that is going to be transferred here. 170, yeah, 170 kVs by improving from 150. So this much voltage profile that we are getting. So also active power transfer that we are getting, it's improved from 17.5 to it's almost 23 point something. Yeah, active power transfer is getting improved after triggering it at 0.4 second. We are triggering our TCSC, and this is the active power improvement that we are getting. So this is a typical graph of voltage profile without TCSC, and this is with TC. You can see how much is the difference, and this is the comparison. So 150.05 was transferring was the voltage conditions before TCSC, and now we are after getting embedding TCSC in series with the 6 and 13 bus system of 14 IEEE 14 bus system, and between 6 and 13 bus. Yeah, the voltage profile is getting improved from 170 to 170, yeah, 150 to 170. So this is the comparison of active power with without TCSC. Without TCSC, it was 17 point almost 96, and with TCSC, it's 24.05 megawatt. It's going to be a difference of almost 21%. Yeah, different power we are transfer capability is getting improved. There's no any transformers being involved, only TCSC FACS device with its simple structure of 3 phases getting involved, and wiring unit and simply a control unit of PI controller we are basically using. So this is a simple graph. So here's future recommendation that we are basically recommending in future. So PI controller can be changed into physiologic, and Power transfer can be improved more, even voltage profile also can be improved more by changing this. We have used a PI controller. It can be extended to physiologic controller. So system also can be enhanced from 14 to 33 bus system and more even. Yeah, we can make it more complex and more bigger one and more real time based. Basically, it's 14. We can increase it to. Obviously, we will have some troubleshooting involved. So in the by using TCSC also we can involve some other algorithms like wall optimization algorithm, weight improve, particle swarm optimization, also more efficient and compatible compensation we can do by using these these algorithms. So these are the references that we have followed presenting this. And thank you very much for watching this. Do visit our Facebook IEEE CBU and IEEE CBU and subscribe and follow us. Subscribe to our YouTube channel and follow us on YouTube. Yeah, thank you very much.